Hi, I'm Vivek Gupta, and I'm going to talk about the overall project flow. Our project focuses on unsupervised cross-model abnormal detection using paired CT and MRI brain images. The overall idea is simple, that we start with paired CT and MRI scans. We pre-process and normalize them so both modality and are comparable. We train a model only on normal data, and the model learns how normal CT and MRI scan relates to each other. During testing, if a scan cannot be reconstructed well, or if the CT MRI relationship looks inconsistent, we flag this as an anomalous. So instead of teaching the model what disease looks like, we teach it what normal looks like. And anything outside that becomes suspicious. Now I'm handing it over to Akshay.
Hi all, myself Akshay here. So I will be explaining you the key insights from EDA. So during the exploratory data analysis, we observe several important things. So the observation points are like the CT and MRI intensity distribution was very different. The CT values are more compact and structured, while MRI values vary more in structure. So the even for normal cases, reconstruction reconstruction difficulty varies by modality. Some slices had very low contrast, but which would confuse the model. So the pair allegation is critical. One small mismatch between the CT and MRI can affect the latent consistency. To help, we decided to normalize the CT and MRI differentially to use a shared encoder to encode the learning moment and anatomic structure. To include a cross-model loss. So these are the techniques we use in the key insight for EDA. So for where we will be exploring to the point.
Okay. So, hi all. My name is Bhushan Kumar, and I will be talking about the modeling part which we have did in this, assignment. So, we designed a shared encoder decoder auto encoder architecture. So, both CT and MRI are passed through the same encoder. The encoder produces a latent representation. So, as you know, like latent representation is nothing but the space where we are reducing the dimension of the actual, the data we have. So, in every image, every pixel is one feature. So, suppose we have 256 by 256 image, so there would be 256 by 256 256 multiplied by 256 dimensions, right? So it is huge dimension. Now we want to reduce the dimension, so we use the latent representation, and we use this autoencoder architecture. So there are many other architectures as well, like PCA, right? So this is a neural network, a way of kind of reducing the dimensions or dimension of the data points, right? So yeah, we like every so both CT and MRI are passed through the encoder um, for the latent representation, and then decoder constructs each modality separately. Okay, so here modality means like CT and MRI. Okay, and then we computed reconstruction loss for both CT and MRI, latent inconsistency loss between CT and MRI embeddings. So the total loss ensures good reconstruction, meaningful shared representation, cross-modal alignment. Additionally, we extracted latent features and trained isolation forest, one class SVM. So both of them allowed us to compare deep learning based anomaly scores with classical one class methods, right? So basically, if we are able to reconstruct the image without with minimum loss, then there is no anomaly. And if we are there is a more loss, there is more loss in reconstruction, then there is anomaly. Yeah, so now I'll hand over to Amit for the next part.
Hi all. I think the next part would be done by Kunal.
Myself
Kunal, and I will discuss about evaluation strategy and its tools. Since true anomaly labels were limited, we injected synthetic anomalies by adding localized intensity patches. We evaluated using reconstruction error destruction, latent distance between CT and MRI, AUC and ROC scores, and what we observed, anomalies samples consistently had higher reconstruction error. Cross-model latent distance increased significantly for abnormal samples. Combining reconstruction plus consistency gave better separation than either alone. This shows the model successfully captured both intramodal structure and intermodal relationships. I hand over to the Amit.
Hi all, my name is Amit Gawande. I'm going to talk about what is the main challenge that we faced during this assignment. The main challenge was not building the model, but ensuring the cross-model consistency that truly reflected the anatomical alignment rather than the enforcing into the artificial intelligence similarity. When the consistency weight was too high, the encoder collapsed into trivial representations, and when it was too low, the modalities diverges and meaningful cross-model learning did not occur. In addition, misalignment in the paired data could lead to the false anomaly detection. Achieving the right balance between the reconstruction loss and consistency loss that required the careful experimentation that we did. This highlighted the broader challenge in unsupervised learning without ground truth. The quality of learning depends heavily on designing objective function that accurately capture the real world structure. So it's all about the main challenge that we face during this application development.
Okay, so now I will go ahead and then show the code executing in VM. So as you can see in my screen, I've logged into virtual machine provided by Bits, right? And I've opened, this notebook file in Jupyter, right? And I'm going to execute this Jupyter file end to end. Okay, so I'll restart the kernel and run all cells. Okay, so it's gonna start. Yeah, as you can see, this is in progress. So this is the first import cell where we're importing different packages used in this project. So before that, I would like just to show our team members. So we have Akshay, Vivek, Kunal, Bhushan, and myself, and then contribution for all of them is 100%. So their student IDs are also mentioned here. So yeah, we have taken up the problem statement number 2, unsupervised cross-model anomaly detection in brain CT MRI images, right? Our group number is 39. Yeah, so now let's go through the code. The code execution is in progress. I will show one by one. So yeah, first one is the import statements. So this include all the packages which are required in this assignment, right? So it needs data loader, data set, right? Matplotlib, TQDM, isolation forest, and ROC AOC score for metrics comparison, right? So first we checked whether we have CUDA machine available or not. So yeah, as you can see, it is using CUDA in virtual machine. Then we set the paths for the CT and then MRI images data sets, right? So this directory in virtual machine contains CT images, and this directory contains MRI images. So basically, we have downloaded all data sets, all images actually from the Kaggle, and then stored into the local machine, virtual machine, right? So we are going to resize the image by 128 by 128, and then batch size would be 16. So as part of the first in the part 1 of this assignment, we have to do pre-processing and augmentation. So every intensity value of image is going to be normalized between -1 to 1. So these are the normalization step for the CT and then MRI, and then we are doing augmentation as well. Okay, so now we have a dataset class, which is nothing to load the data from the local drive, right? And then going to resize and then normalize. So above cell contain the method only. Now it is actual execution happening here, right? Then we have loaded the data set here with this method data loader, and then it is going through the convolutional autoencoder, which we discussed in the beginning as part of the architecture, right? So we have encoder architecture and then decoder. This is the forward pass, right? So as we can see the convolution and then ReLU function being used here in the encoder, and transposed convolution used in the decoder, right? Now these are the modal initialization. So we are using ADAM optimization, right? So the encoder has been initialized here, decoder also, and then optimizer being used as an ADAM. Okay. So now we are going to run the encoder decoder with 20 epochs. That's what we have decided, and what we have observed is the loss gets consistent in 20 epochs. So I can show this, right? So this is epoch 1, which is started from 0.73, and it went to 0.59 in the second epoch, and then 0.54, and here we can see it is consistently coming to 0.53. So kind of we can see that loss is consistent here. Now we have reached out to saturation. Okay. So now coming to the reconstruction error. So this is the method which calculates the anomaly score, right? And we in this method we are injecting the anomaly, and then we have a method for the isolation forest on latent features. This method. Then coming to here, and then this one. Yeah. And then finally we are going to visualize the anomaly map, right? So as I discussed in my part when I was talking about the encoder decoder architecture, where we saw that if there is high reconstruction error, then there would be anomaly. If there is less reconstruction error, then it won't be anomaly. In this image you can see, like, if the after training one sample input has been taken, this is the sample input, and then we got this as a reconstruction, going through this encoder and decoder architecture. So this is the reconstructed image and this is the input image. So this is nothing but the input minus reconstruction. So this is the image. um, uh, there is no visible anomaly in this image. Okay, so we do not see any dark and bright spots, right? So we can say that there is no anomaly in this picture. Okay, now we had to train the model using three methods, right? So one was the encoder decoder, the second was one class learning, right? So this is the code for one class learning, and this is for again this is again the part of the one class learning as well. The third method is cross model consistency based detection. Yeah, so this is the method for cross model consistency based in detection, and then we are injecting the anomaly, synthetic anomaly. So yeah, this injection is happening here, and then finally we have AOC ROC calculation for all of the three methods which we have defined, right? So we can see here, um, and then I think we can see in the final comparison well. So if we come here, the AOC ROC curve for autoencoder reconstruction is 0.4880000, and for one class SVM it is 0.468035. For cross model consistency it is 0.497013, and then mean reconstruction error is, so mean normal error is nothing but 0.0024197, and then mean anomaly error is 0.002369795. And we can see the reconstruction error distribution as well. So the blue one represents the normal reconstruction error, and the orange one represents the synthetic anomaly. And in the final one we can see the isolation forest anomaly scores, right? So, and then this is cross model latent distance distribution as well. Yeah, so that's the end of the code execution. We could see that it is running live running of this code in